again in the fall. Good or bad, we talk about some thermodynamics and some aerodynamics at that point. But today, I want to have Ali talk to you about composites. This is an area that he works, has worked and is working a lot in, so I think we have a really great talk with Ali in terms of composites. We're going to focus more on the basics that you should have for this topic. We're not going to get too much into the detail, but if you really want to get into this and dig into it, feel free to set some things that we can go through with that. Now, before I turn over to Ali, just a few quick announcements. So your lab is almost done grading. You should know the results of that by the end of this week. The exams have been graded. You can pick those up from TAs or myself during office hours. Just come by and you can get those. Wednesday, we will not be introducing any new material. Everything that you need for the exam is up until the class today. So on Wednesday, we'll do all the typical review. And if there's any questions in particular that you really want to get covered, again, make sure you send me a message or something so I can make sure those are on the list. And I get to cover those before we see them again in the final. The past exams have been uploaded to Canvas in the practice exam section, so make sure you check those out also to help you prep. Yes? Average on the last exam was a 75 and a half, I think. So 75 and a half was the average percent. Okay, so now I'm going to hand you over to Ali. Now, you should have gotten an email from me earlier today about FCQs. So about 40% of the classes have already filled them out. If you haven't already done so, please make sure that you get in there and do that. It's important. We use this to evaluate the course, evaluate the instructors, check on how courses are improving, see what areas we need to improve, and then monitor it as we go. Okay, questions? The practice exam, so yeah, of course, for the last, I think it's the last 3 years. So you should have 17, 16, 15, and I think 14, right? So you should have a few to practice with. All right, so I'll hand you over to Ali, who's going to go through the fundamentals of composites.
You guys hear me? Cool. So I'll get started. I promise it's not a lot of new concepts today. It's a very short class. We can actually boil it down to one equation, which is going to be important. I am not going to go through a lot. It's just going to be an interesting class, and just to wrap around what we've learned through the semester so far. All right, so ASEN1022. What have we covered? There were concepts that we learned and the skills that we gained throughout the class. We started with the nanoscale of atomic bonding. We learned about primary and secondary bonds, what's the difference between ionic and covalent, and then we actually zoomed out a little bit to the microscale and discussed crystal structures. So with crystal structures, you have different FCC, BCC structures, and then we discussed their defects and dislocations. We zoomed out further from the nano to macro to micro, all the way to mechanical properties, where we actually examined materials and their stress strain. We looked at failure, whether it was fatigue or fracture. And then we also discussed important topics for materials. Materials are not used for for their structural properties. They're used for everything. So we discussed diffusion as well as thermal behavior. And in the last month, we talked about phase diagrams and how important they are in terms of mixing materials together. And then we also discussed what type of heat treatments or thermal behaviors materials undergo. But with these concepts learned, every concept we saw actually had an issue with it. You guys remember atomic bonding? What might be an issue for us? Does anyone think what can go wrong in atomic bonding? Anyone wants to answer? raise their hand? Yeah, go ahead. Vacancies is one. So with atomic bonding, there are weak atomic bonds, vacancies that can actually create defects on the nanoscale. And we don't like that. What about crystal structures? What can go wrong there? Okay. Yeah, go ahead. Sorry? Grain boundaries. What about grain boundaries? True, but there were an aspect of crystal structures lining along together that were very important. We called them one name. What did we call them? Dislocations? Yes, exactly. So dislocations or imperfections in crystal structures can cause a lot of problems. And with diffusion and thermal behavior, we can have undesirable diffusion or thermal behaviors of materials. Also, with mechanical properties or failure mechanics, we can see the difference between the really undesirable brittle material and the very desirable form of a ductile material. And then with phase diagrams and heat treatment, we can unfortunately have improper mixing while we're mixing two materials together. If you guys remember phase diagram, material A, material B, your alpha, beta, gamma phase. Or with heat treatment, we might not have as well as a finish as we wanted after machining a part. So, and there were other material issues. Can anyone think of other material issues that we covered? Yeah. Stress concentrations can be an issue. Yes. What else? Cracks, which is also from fatigue or fractures. One thing that we covered is some materials tend to be tough but heavy, like metals, and we don't like that. And some materials tend to have a high strength but brittle, and we don't like that. Corrosion, like we covered in last class, Dr. Jackson spoke about corrosion and erosion effects. And then catastrophic failures are things we wanted to avoid, right? All right, what if I tell you, let's forget about all of this, and actually throw all materials behind and design our own material? Wouldn't that be cool, right? It would be, right? And the answer is composites. The composites came in the 1950s or even before to change or tailor the material to our desire based on our application. So composites are engineers' attempt at customizing materials to tailor fit for applications, like I said. So rather than looking at these properties as actually issues, we look at them as a design checklist or a guideline for us to actually cover every topic, go to atomic bonding and see what can we improve in our composite. Maybe get to mechanical properties. Do we like the material to be tough or stiff? Well, if it's tough, can it sustain high temperatures? Is it okay for it? Is it okay under environmental conditions? So composites are the engineer's dream to tackle a material problem. So for the lecture goals today, I want you guys to get motivated about composites. You're very excited. And to know about the rule of mixing. The rule of mixing, which is one equation that is very important that we're going to derive. And then if we have time, we're going to go through a very quick case study, which is actually, I can actually relate all my research to all the concepts you guys have covered. So we'll just get through this and then try to break it down rather than chapters, but more of an integrated material problem or material. All right, so let's start with composites. Actually, when scientists started debating whether composites will work, they were actually faced by a huge problem. Oh, national materials are already there, so why actually make our own, we can mine for them, but actually nature has proved to us that composites are the answer to all of this. Trees are considered composites. Butterfly wings, you have structural shapes and then just very light, thin foil that actually can move the air to lift off a butterfly. Our bodies are a composite. We are not made of only bone. We're muscle, organs, tissue. That's why we can move. And also spider nets. There are numerous examples of composites around us. For the aerospace industry, we actually get so excited about this. You guys know about the VFR? Isn't it exciting? This is going to be made out of composites. Also, I'm sure you guys are sick of these two airplanes, but can someone tell me what the KLM airplane is? 787? What about the one in Singapore Airlines? A350. So both are the leading edge twin engine planes that are actually taking over the aerospace industry. Forget about those jumbo jets, the 747 and the Airbus 380. These are actually scheduled to go out of their production for these guys to go in because of their efficiency. Any aerospace geek that can actually guess what this engine is? What? Sorry. Sorry? That's a GE90X. So that is the engine that goes on the 787 and the upcoming 777. And the engine itself is 70% composites. All right, other quick examples in engineering. It's not just the high-end stuff. Maybe it's the high-end aerospace, but buildings are composites. And race cars can be composites. High-end road bikes and even performance prosthetics for races. These actually prosthetics actually are faster than the natural human body. You can reach and actually make world records with these prosthetics. All right, so let's look at this diagram together and see where composites lie and where other materials lie. So if we look together here, the specific strength to weight ratio increases, and the stiffness increases from bottom to top. So you have metals that are slightly less, they are strong, but their strength to weight ratio is not as good as ceramics. While ceramics are strong, yes, and light, but they're brittle. You can't just fly rockets with a ceramic on. So we have to merge both and actually, sort of, if you wish, cherry pick between the advantages that materials offer and the toughness or the strength and the lightweight that ceramics offer. Another way you can look at this is the toughness and the strength. Ceramics lie, yes, they're very strong, but their toughness suffers because of their natural brittleness. And like if they were just ceramic, we're not talking about composite yet. And then metals are tough, but they lack, or not lack, but they're not as high up, as strong with ceramics. So composites tend to push the boundaries by combining both for further applications, high temperature applications for, like, as I'm going to show later, for atmospheric re-entry, that metals can't really sustain, so we're bringing ceramics with metals in here. And what research is doing right now is actually trying to expand this bubble. So if you would like to expand it, your desirable direction would be further on, increasing strength to weight ratio and increasing your specific stiffness. Same thing over here, you'd like to move in the diagonal direction up here. Cool. So as we said, composites are artificially made by two or more materials. However, their constituent phases are chemically dissimilar. So they are separated by interfaces. Now let's just pause for a second. Alloys have two different materials and composites have two different materials. So what's the difference between the two? Can someone guess? Go ahead.
Alloys are two different metals, whereas composites might be metals and ceramics.
Composites can be metals and metals, too. You're close. But they're major. Think phase diagrams. Go ahead.
Alloys are a homogeneous mixture.
Okay. Yes. So, you want to elaborate on that?
Composites are like heterogeneous.
Okay. That's good. That's actually a very close answer. So, the answer to this is that if you look at phase diagrams, remember when we dealt with two materials, one starting at 0 material A, going up to 100, while your material B is at 100 when your A is at 0, and you tend to mix the two in liquid form and then pull them down and maybe get to your eutectic or eutectoid region to achieve a certain alloy. These are alloys. You're actually mixing two materials, usually metals, in a molten form to reach an alloy. While composites, as you can see here, they're actually two different distinct materials in solid form, not molten. We're not mixing them. They're in solid form, and then we're just laying them in a way that better achieves properties for a certain application. So as you can see here, there are fibers and a couple of other matrices. These can be either metals, they can be ceramic, they can be plastics. Since we're creating our own, we're free to do whatever we want. So, just before we dive into math, let's just talk about how a composite is formed, or what's the two main things that we can find in a composite. The first is a fiber, and those can be seen by the inside over here. And around them are a matrix. Is a matrix. So a fiber's main purpose is usually to reinforce a material. They're usually more dense. They're stronger than matrices. However, a matrix actually serves two purposes, which holds a particle or a fiber in place at a favorable orientation, and it also provides some ductility to maybe a brittle fiber, so that you have the advantage of both worlds. Maybe your fiber inside here is a ceramic that is brittle, but survives high temperature, and your matrix can be aluminum, which is a little more ductile, and actually can bounce back and forth with a higher Young's modulus than ceramic. Sorry, lower. So fibers and matrices are bonded together by an adhesive, and usually that adhesive is embedded in the matrix, or they're just mechanically loaded together. They don't have to be like adhered together. They don't have to be very strongly glued together. And that is outside the scope of the class. We won't discuss that. But. So with fiber reinforced composites, we have 4 different layouts. We can have a continuous aligned fiber like this one, and a discontinuous fiber that is also aligned, discontinuous random, and then we can have a textile woven fiber composite. Those are common examples. Fiberglass, I'm sure some of you might have heard of. They're put on turbine blades, actually windmills. I shouldn't say turbine blades, it's very general. And carbon fiber, they're used for high-end, very lightweight engineering applications. Cool. So the fiber reinforced composite has 2 main design parameters that influence its properties. So we're free to align the fiber in a certain orientation. So the spatial alignment or arrangement and orientation matters. And how much fiber can we fit in a matrix also is up to us. So those are 2 or different loading directions, and we'll talk about why they are important. You can either have fibers that are aligned that way. Can everyone see my laser pointer? Sorry to cough. I might use the mouse. Actually, so if you align your fibers longitudinal to the load, this is what we call fibers loaded in an axial direction. However, the opposite is if you align them perpendicular to the load, this is what we call a transverse direction. Same thing here, if you just take that piece of fiber composite that we're talking about and look at it from the inside through the thickness, you can align it what we also can call a transverse direction. And these load configurations are very important. Can anyone guess why? So strengths are different in strength. Tensile strength are different in different directions. Yes? And that is exactly what we were talking about. If you have your fiber axially loaded, you'll get the maximum tensile strength out of it. While if you slowly orient the fiber from the 0 degree to a 90 degree, it will actually lose its strength the more and more you rotate it, and provided that you're keeping the same axial load. So this gets us to a point that right now we know that we have two different materials. We know that a fiber has a different property, especially Young's modulus, than a composite. So we will have actually two straight lines in our stress strain diagram. These two straight lines, the first one will be your fiber, and then the lower Young's modulus will be your matrix. But we're now left to the question is, now we designed our dream composite. What is its properties? We're actually lost in terms of that. How do we calculate that? And then can we actually do that? And based on what? What will help us? And this depends on